Okay, so one of the things we had at the end of each day is effectively just the discussion points. So this was some of the points that Will had, and a couple of points that I had as well. There's another slide here as well, which I can add points to afterwards as well. So this is just general topics for discussion that have come up during the meeting. So how can we differentiate wide orbit planets from FFPs? There's a lot of things, whether they could be white dwarfs, whether they could, effectively, are they FFPs is the problem. Then it's like, how do the three ground-based surveys compare with each other? We heard, what was it, NOAA had the 2D versus 1D detection efficiencies. KMTNet has got the new pipeline. We've got lots of things. Is it possible to sort of combine these to sort of have a sort of a unified pipeline to actually then make it so all the different surveys are actually consistent with each other? There's like comparisons with Earth 2.0. Following on from Scott's point earlier, is it possible to develop simultaneous pipelines for FFPs, microlensing for the wide orbit planets? And then one point I had for the future, going on like what Will said about the mass measurements, is also velocities are also quite an important indicator of where planets come from, whether they're binary ejected, whether they're planet-planet scatter. If we have simultaneous Roman and Earth and get the parallaxes and break those degeneracies, we can actually then start saying these planets come from this, these planets come from that. And that I think will be really important and can point to specific formation pathways and can start telling us a lot about physics. So I just open the floor to if you want to discuss these topics, or if people want to talk about a different topic as well that we can add to this list. Sorry, yeah, I was going to have to pass the microphone around.
Actually, I have a question for them. I think when we discussed this at the non-transiting planets meeting at Goddard, I had the impression that Ogle didn't have any plans to do like a systematic study of search for people and planets in the Ogle data, and in particular, going down to Painter host stars. Is that still the case? And would you be interested in collaborations with people who might want to really help with that?
Mm-hmm. So what we did, we analyzed first 6 years of Ogle survey, first 6 years of Huygens survey. That included all types of stars, including and sources. But that was that analysis also only included time-scale measurements. So we created the time-scale distribution. After that, we thought adding additional years of data wouldn't be really helpful because it just extends the data set by a factor of 2, which is not a huge improvement. But we have some students who are working on that now, maybe in other contexts, in the context of black hole searchers. But as a byproduct, we'll probably have a sample of microlensing events from 10 years of data. So we'll try to revisit this. We'll try to revisit the free-floating planet mass function, but it's not high priority for us. Maybe, yeah, we will have some students who can work with that. And if other people are collaborating, well, I am not the PI of the project, so it's a question about external people working on data.
So do you have any opinion on the possibility that Ogle might get a new PI, say if someone were to retire?
I don't think that the PI is going to change anytime soon.
Well, I just, the last point, I think, is an interesting one. And I guess I see, I guess I'm trying to remember if I've ever seen a prediction from the light papers that predict the frequency of free floating planets from, say, being ejected from systems, forming systems that actually show the distribution of velocities as well. Like, I guess I don't think I've ever seen that plot.
So there's one in my work in this year, come out this year.
Okay,
I think it's in that paper, but there's definitely plots that show the ejection velocities and where they come from. And generally, the binaries, if you're ejected by a certain binary, they go out about 10 to 15 kilometers a second. That's where the dispersion is. Whereas if it's planet-planet, it's about 1 or 2. So it's similar then to the stellar population in the star-forming regions, which is why it's a very different point. You can see large velocities or large velocity dispersion and great degeneracy with the distance. That will then point to either binary or planet-planet scatter. And that does also change a little bit with the mass of the objects as well.
right. So the velocity you predict depends on how they're ejected, and then therefore, and since the mass that dominates the mass budget, or the method, the way in which they were ejected that dominates the mass budget to give a mass varies, then the velocity dispersion should vary as a function.
Yeah, so this is something that we discussed in the paper, but honestly, in an ideal world, right, you really care about the mass and velocity distribution, not just the mass function, right? Because there are sort of different demographics within that distribution that correspond to different formation mechanisms. So you might be ejecting, So you might be ejecting more massive things from, for example, scattering off of certain binaries, and those are going to have higher ejection velocities. Now, the question of the actual observability of something like the velocity, the masses span multiple decades, right? The velocities, it might be 10 kilometers per second versus 1 kilometer per second. And I don't know necessarily that Roman's sample will or will not have the sensitivity to be able to pull out those sorts of things. But I think it's at least one open question to me that I think would be really interesting to try to figure out, because it is almost even easier to see what the origin is from the velocity than the mass.
So, of course, the thing that makes it difficult to measure determine the velocities of the free-floating planets in the form is that the velocity of stars that they come from can be fairly high. But of course, the velocities that the stars have actually, when the stars are first born, their velocities are in the disk are pretty low. And so I'm not sure how quickly they're supposed to increase. But the time scale of the ejections would be, I mean, if it takes 100 million years, maybe the stellar velocities are a bit higher than if it takes 10 million. And billions of years.
Stop. Sure.
On this point about the velocities, it seems like you want to age kind of at the same time. So it seems like this would be way easier if you did it for like direct imaging of star forming regions rather than microlensing sample, which is average throughout the disk, because then things that are ejected with a large speed, since the velocity dispersion of stars increases in time, you have a snapshot of planets and you don't know what planet.
It would be a lot easier with direct imaging. Yeah, that is true. But you need to be looking at the cluster at that point as well, which is the thing. But it should be, if it's in the microlensing data, then that'll be a handy thing as well.
Yeah, I guess the challenge with direct imaging, we're going to hear about direct imaging on Friday, is just the fact that if you want to probe the low mass end of this FFP mass function, I mean, I don't think these things are going to be luminous enough to do direct imaging on. So it's useful for formation mechanism of, let's say, super Jupiters versus failed brown dwarfs, trying to characterize that Einstein desert. But I'm not sure as you push towards the lower masses, if we're looking at Pluto's, for example, you might be forced to use microlensing to try to figure out their origins.
But if you wanted to do it on microlensing planets, I'm not a galactic dynamicist, but I believe that the typical velocity dispersion, at least in the solar neighborhood, is like 50 kilometers a second.
Yeah,
So trying to find something that's 10 without an age seems kind of.
that was kind of my point about the decades of mass versus very marginal differences in velocity. So again, it would be ideal if you could do it, but I'm really not sure if it's achievable.
So I'm not sure about I guess it's the velocity dispersion may be depending on the possible host stars, right? The smaller velocity from the lowest host star, I guess, wasn't it? And if that case, there is degeneracy between the typical host mass and also the age and some other parameters, even if we measure the velocity dispersion of the sample.
Yeah, I'm not sure how it changes with mass on the data. I need to look.
So I think a simpler way to think about this is just, can we measure the difference between the velocity dispersion of free-floating planets and the velocity dispersion of the stars? And we're going to measure the masses of the free-floating planets and the masses of the stars that are causing microlensing events in very much the same way. So that'll control a lot of the comparisons, right, in terms of the population. So I think you should be thinking about not measuring. I think you should be thinking about, if the velocity dispersion is 10% larger for the free-floating planets, is that detectable? And if we can break that down into 3 mass bins with enough free-floating planet mass measurements, does that tell you anything? And I suspect the answer is sure something, but you know, maybe not. It's not going to revolutionize it. It's a relatively easy calculation is to ask, how well can we measure the velocity dispersion of the sample planets with mass, free-floating planets with mass measurements from contemporaneous ground-based observations?
So any other points for discussion or discussion points? Okay. Oh, no. Okay. Sure.
Just a quick point on the first line. So I showed some work on Keck analysis with FFP candidates. A little bit of some self-promotion, if I may. Also, there's a precursor HST survey that will take high-resolution HST images of maybe 40 or 50% of the Roman GBTDS footprint, starting February. So similar to the work I showed with Keck, getting a very wide area imaged with HST high resolution before Roman may detect some of these FFP candidates might help get toward that disambiguation. But yeah, that's not a question, but just an idea to think about. We'll go pretty deep.
So if anyone has any industrious students, the first point, so you can estimate the how far a free-floating planet would have to be on average from its host star before you would not see the magnification view of the star itself. Those calculations have been done for ground-based surveys, but I don't think it's ever been done for Roman. And so you could ask how much better you can do with Roman, with cadence and photometric accuracy with Roman, and I think it would be a cute little short project to do that. Just a thought.
Actually, it's got I have a student who is doing that. So within a few weeks, you should have some.
All right, good.
So I was just chatting with Kokubo-san, and there must be many embryo around the star forming stars, and there is no way to detect. So I was wondering, is there any possibility to detect such, like a Mars embryo by some way with the microlensing or any other method?
As in no still bound, or just FFPs?
It's there must be the bound embryo, but also that many of them might need scattered out. So for the mass, the Roman may have a sensitivity by the microlensing, right? So if there are many of them, we must be detectable.
There's definitely a lot of them in the formation model.
Yeah, and if they are around the lensing zone, around the ancient radius, around the host star, we maybe detect such a small object. But I'm not sure how it looks like if there is many of them around the stars. So it's multiple, many lensing problem.
Yeah, so you're asking if you are looking at like a very young star system that has a ton of Mars mass embryos around the star, in principle, Roman will be sensitive to lensing events in that system. But you might also have, hundreds of these small Mars embryos, and what does that actually look like in Roman?
But Einstein radii are very tiny. They're like close to the stars at least. So there could be a lot lower. Then Einstein, if they're like separations large than Einstein radii.
Yeah, just a very random question. Is it possible for Roman to detect any free floating planet's moon? Given that moon is roughly the mass of Pluto.
Yes.
It's possible.
There's a paper by Sanjida. Yes, there's a paper on the second century.
It's a jetty.
It's the jetty.
No more.
Yeah, going off the Mars embryo question, are you talking about ones that are bound around the protostar?
Yes, those bounded and some of them are scattered.
Wouldn't the bound ones just be too embedded to be able to see any signal? Like if they're still really
In the disk.
Yeah, right. They'd just still be embedded, so you wouldn't be able to detect them that way. Or am I thinking about this wrong?
So yeah, it's a good point. So if there's really a bazillion embryos around, around each star, then I assume, like we're hearing, like while the gas disk is still there, there's enough good candidates for microlensing anyway. So it's kind of what's the earliest age that you'd expect to be able to possibly see a planet by, see things around a star by microlensing. So I assume that if you can't, you definitely can't do it while the gas disk is present, I assume. If that's the case, then by then, there would be only a limited number of larger objects that should emerge from the star.
Do we know the answer to that? What's sort of the youngest system we think that we can actually do lensing in is
As a lens?
Yeah, as in, so imagine you have a bound system, right? And it's a very, very young star with a protoplanetary disk around it. It's got embryos or whatever. What do you need the entire disk to disperse before you can do anything?
Well, I mean, any system can serve as a lens. It's just that young systems towards the galactic bulge are extremely rare, and those that are there are going to be typically in star forming regions. So there's no stars behind them. Right? You're talking about, So if you just happen to have a young star that floats along your line of sight through the galactic bulge, you can serve as a lens and you'll see the microlensing event and the disk.
But will you see like a substructure of the disk? Or is it such that you would only see the sort of overall resolved?
If you have an unresolved, if you have an edge on disk, the optical depth is high enough that you can get interesting lensing phenomenon, maybe, but it's pretty low. Again, I can point you to references that people.
Okay. Jeremy.
So I'm a newcomer to the free flowing planet scene. A question on the first point. I heard today that estimates about 20 free flowing planets per star that has Jupiter planet, or is that the rough estimate, right? So what's the probability that a free flowing planet would encounter a star, another star, like flyby? Because one way to, so I've done a lot of work on stellar flybys, and the question is, can we disentangle between a flyby that's actually unbound, like a planet's unbound, or is it actually a long period bound binary? And so one way to do that is look at the disk structure, the signature that the flyby candidate leaves on the disk. And from the disk structure, you can kind of infer, disentangle whether it's bound or unbound. So maybe this is a far-fetched point, but is it possible that you have a lot of these free-floating, you have a huge population of free-floating planets, would they, again, they maybe encounter a star with a disk in the future? Is that, what's the probability of that? And you maybe use that to disentangle whether it's bound or not. Because even from simulations, you can attend Jupiter mass planet, you can see the signatures that's left on the disk from that planet.
So, I mean, the large population of free-floating planets is supposed to be dominated by low mass planets. There was an earlier paper suggesting, but those are giving signals about a day, and there are things related to the Earth that give signals around a day, and some of this is signals with systematic errors that have now been corrected, and we don't see any evidence for a large population of Jupiter mass. So, but yeah, I'm not sure. I mean, I think, you know, effective flybys.
Yeah, I can put some numbers on it if you want. I just looked into this not too long ago. So there's a 1% chance per billion years of a star in the sun's neighborhood coming within 100 AU of the sun. So if there was 20 times more stuff, then it'll go up to 20% per billion years of something passing within 100 AU of the star. That helps it.
Yeah, I mean, that's way past the disk stage, right?
Yeah, it's later on, and so it's a different realm, but still, you still wouldn't expect them to be coming and messing with planetary systems every day.
So, for the galactic population, sure, but what about in star forming regions? I mean, if you have something like the LHC, for example, where, it's 2-3 million years old, and it's really dense. If you have things that have already been ejected, I guess you're more likely to have a star mess with the disk. You fly by than a planet, but if you have 20 times as many planets, then would you be able to see that, like, all night or something? Okay.
Oh, I can comment on that. So there's this hypothesis that the solar system may be born from a star cluster. And the flyby frequency within a star cluster is roughly, like the closest flyby is about 200 AU or something. Yeah. So if you scale this with like 20 times more objects, that gives you, I think, roughly square root of 20. So that's, yeah. It should be 200 AU divided by 50. So it's like 20,
200 AU divided by
square root of 20.
Most of them would be very small things.
Okay, Scott.
I have a somewhat unrelated question, but, so one of the things that is cool about microlensing is that you can detect, planets around stars all along the line of sight to the galactic bulge. So that includes stars in the galactic bulge and in the galactic disk, and free floating planets in the galactic bulge and the galactic disk. Are there predictions for how the free floating population of planets might change if they're part of the bulge or part of the disk?
I don't think I know it in minutes. It is something I would look into in the future, though. On the methodology of that, at least. Yeah. That's,
I mean, the thing that got me thinking about this is that there was a paper by colleagues of mine at Ohio State University, Todd Thompson, who wrote that giant planets might be rare in the galactic bulge because the radiation environment is such that the temperature of the protoplanetary disk is above that of the ice line, and so you don't ever have solid water, and so that's one. So it could be that. So I'm just thinking there might be analogous things to dynamics, either formation or a number of flybys in the galactic center, or those kinds of things that might change the population of people.
yeah, it will change quite a bit on the radiation environment because that effectively kills it's more the UV that kills the disk rather than natural formation, which truncates the disk and removes all your dust and pebbles. So that I would expect that there should be differences. Well, they are, and it's still
So just complementary comment. So we just set the prime observation that there is a near infrared microlensing survey, including the survey area is including the galactic center. So maybe the survey is just started. So maybe we will measure the difference of the FFP population compared to the optical microlensing.
Just to give like theoretical comment to Scott's question. So one of my students looked at thick disk, it's not bulge, but thick disk versus thin disk. And it's kind of related to what Todd did, but for the thick disk, and I think it's similar to the bulge stars as well, but they originate from the earlier stages of the galactic evolution. So that is a really different radiation environment. It's like starburst galaxies. So you are in a very extreme environment where you will very quickly get rid of the disk. So you will probably have much reduced population of the giants. So if giants do participate in ejecting the small planets, then that might suggest that you might expect some reduced population of free floating planets as well. What is a bit unclear is like what that does to the primordial rocky planet population, because this is more relevant for the gas dispersal, but it's a bit unclear what exactly that does to like solids. Like it might change like the volatile species, but not necessarily the refractory species. So that part is a bit unclear.
just that generally the problem is the pebble drift on affecting the rocky planets. Because as soon as you get rid of the gas disk where you truncate it, you can have your dust and your pebbles still sitting at 50, 80 AU, but there's no gas for it to interact with, for them to drift in and to accrete into planets. So it kills the planet formation in that way as well as just getting rid of the disk. That's generally the case of what happens. And that's not even going into the starburst galaxies, which are even higher G0 and higher UV.
Since I have a mic, I have a question. Kind of related to the first point. I think Scott was mentioning in his talk, but there's a possible false positive for FFP that's flare related. So should there be another point there that is wider planets, FFP, and something else?
I'm probably going to take this.
Yeah, so I have been working on a project of looking at test data to try to find any sort of microlensing candidates, right? And one of the things we found in the first sector that we looked through was an event that looks very, very strongly like what you would expect for a like an FFP with finite source effects, right? Problem is TESS is not designed to be a microlensing survey, and so the rates you would expect are just, I mean, this would point to some very, very high abundance of FFPs, and so it's much more likely to be a false positive. Prejmek looked at longer baseline local data and suggested the star might have magnetic variability on it, so this could be associated with a flare. However, the issue is that it really doesn't look like any of the flare models that exist. And so because of that, it's sort of it's likely a false positive, but whatever kind of false positive it is could be a very pernicious one in the future for trying to disentangle from legitimate FFPs in Roman, for example. So yeah, asterisk there, I guess, is there might be other backgrounds that are also challenging to mitigate against.
So I had a question. So what is the color of the star that's associated with this flare? I mean, there was, we had a strange event that was sort of well fit by a very low mass planetary model in the MOA 9-year sample, and we asked Ogle for their data, and you also pointed out that star there was very red, which makes white light flares are much more common in red stars. And so, we talked to some flare experts and said, oh, flares are really rare, and you expect to see only every 400 years. And that may be rare to people who study flares, but lenses have really, really common. So, things like diagnostic technicolor stars.
Yeah, no, this is a very old giant star that, again, to your point, is not supposed to be flaring. But also to a flare person, not supposed to be flaring is in the lifetime of them looking at it, not in the sort of microlensing scale lifetime. So it's possible that even these stars, every once in a while, have some, very energetic eruption. The energy associated with this event, if it's a flare, is very large. So it's also sort of unusual in that respect. But yeah, it's entirely.
What type of giant star is it?
So I don't remember off the top of my head. It's in the paper, obviously.
It wasn't like an M giant.
Is it brighter than the clock?
I think it's.
Yeah.
Because, I mean, well, I mean, a lot of the events we've been talking about from the ground, a lot of those involve giant stars. And so if this is I mean, for giant stars, we should be seeing things like that if they're much more common than you expect from the free floating planets. So, yeah, so, I would wonder why we haven't seen many of those, or whether some of the ones we're claiming are actually.
That's something that I'm also wondering, because I think given, so this is one event in 7.8 million light curves over sort of like a separated baselines, because TESS observes in this weird way. So yeah, it's kind of hard to know how to compare directly to what we would expect it from the ground. But yeah, I would have expected to see a lot more of these sorts of events as well.
So which paper is the one describing the flare?
Yeah.
Whose paper? I mean, there's several papers.
Oh, the original archive posting by me and Michelle and Nolan, which is still not published. So I can show you a much more up-to-date draft a year later if you would like.
Okay. Yeah, so I mean, the events that like Ogle or Hampton are finding, they have a much longer baseline data. So, if these things happen every once a year or something.
Although, when we were chatting earlier, you had said you didn't see anything in the Ogle data, but you're also sampling at a different cadence. So yeah.
Okay, when we talk about this specific event, the test event, it was observed by Ogle and for like 2 years or so. With low cadence. So what we detected was like semi-regular variability. This is typical for like spotted stars. And whenever you have spots on the star surface, you also expect flares. And this is what I like discovered when I was working on the Ogle paper, the pre-floating planet paper, that there were some short-lived events, but in the light gap, you could also detect variability due to star spots. So these events were rejected. Well, I don't think these are genuine maintenance events. We have also, my colleague was also working on spotted stars with Hubble data. What he had found, like a few hundred spotted stars with variability due to star spots. Some of these objects also showed flares. I think that in at least 2 cases, there were instances of symmetric flares. Usually, if you have a flare, it goes up very quickly and then falls slowly. And there were 2 instances of non-symmetric flares combined with variability due to star spots. So from observational point of view, I have seen such objects that usually as.
Yeah, no, and that being said, unfortunately, because of the low cadence observation, like the light curves of the symmetric flares or whatever are very poorly sampled. So it's in comparison to the test one, which was drilling at like 2 minutes, where you really see the symmetric feature. I totally agree with Prejemek that like if we were to look, for example, maybe if Ogle did like a dedicated survey or a dedicated review of the spotted stars, and then was trying to figure out whether or not these sorts of events persisted, maybe you would find more of these things. But it's also a little bit challenging because this is a fairly short duration event, so to characterize it well with low cadence data is tough.
So I would suggest that it might be worthwhile publishing some of this stuff on the relationship between these flares and spots, and also, I mean, it's related to people have been arguing, for example, that the giant stars are the best sources for studying free floating planets, and I think there's a lot of potential problems with that. Some of them have to do with spots, and so I think a paper on the sort of stellar activity background to free floating planet detections would be pretty useful.
So I have to stress that in the case of the test candidate or other stuff I was talking about, you can see clear variability due to star spots in the data. In the case of free floating planet candidates that we published over the years, we see no signatures of variability in the larger data. So these are basically flat to a high level of precision. And also the amplitudes of microlensing are larger than in the case of the test events. In the case of the test event, I think the amplitude was 0.1 or 0.2 magnitudes. It was pretty low.
Yeah, 5 to 10, like 5% or something.
Yeah. Whereas the microlensing free floating candidates that we have found have amplitudes up to 1 Mach or even larger after the event. So we are like pretty sure these are genuine microlensing.
Well, yeah, and I think that also actually brings up a question that I had maybe for Scott or Dave, which is, one of the nice things about Ogle is they have such long baselines of data, right? And so they can go and make sure that this is a really, really flat star. The light curve looks really good. When Roman launches, I mean, we won't have that kind of baseline yet, right? We're going to be sort of bootstrapping up. And so we're not going to be able to rely on these super long baselines to feel absolutely confident that, there's not some very long-term periodic variability. Do we have strategies to mitigate against this right now?
Well, first, I wanted to just respond to Semek's point that I would suggest it would be useful for other people who don't have the experience in analyzing Ogle data. If you publish something that details about some of these false positives, since you're the one that knows about it, you're not you're probably the least likely to be fooled by those false positives, but it'd be useful for everyone else to, you know, spread that information. I mean, I think, you know, for the Roman data, obviously, I mean, we have this problem whenever we start up a new microlensing survey. You know, MOA tried to alert in the very first year in 2006, and you know, there's a lot of interesting events that we didn't alert on, and we published papers much later. And you know, OGLE, when they started up OGLE 4, they didn't issue a single alert in 2010. They had data on a lot of good events, and so, you know, what's going to happen with Roman is, you know, there's going to be a lot of things that we can do with the data that we need more than like one season. So, you know, I mean, similarly, you know, when Kepler launched, right, they published their first paper on you know, discoveries that weren't super novel. I mean, some of them were already known to be transiting planets, and it took a little while before. You know, before they really took off. And you know, for us, right, I mean, like mass measurements of the host stars, if we're getting, you know, if we're detecting the host stars separated from the sources, then we get a lot more information. So, you know, so I think, you know, we can have a few, you know, we can publish papers on, you know, free-floating planet candidates, but we just have to be, you know, more cautious about it and detail you know, how we're going to confirm discoveries.
And also, if I may add, an easy way to understand if it's a free floating planet or not is with a microlensing parallax.
Yep.
Which is what I'm going to discuss on Friday, but yes, if it's a flare, you won't have a parallax effect. So this is the most certain way to know that what you have is real or not.
No spoilers for your talk, but yes, parallax observations would be great. We really want simultaneous observations.
I think maybe a more general answer to your question, Will, is that, you know, I think with the long baseline of a lot of the ground-based microlensing surveys, you know, basically these events, you know, it's microlensing because the star has done absolutely nothing except for this one brightening or maybe two brightenings that are separated. We're going to have to rely on something a little bit more nuanced with the Roman data, and that, as Dave is implying, that's going to change over the course of time. So I think their initial discoveries are going to be things that are either extremely high signal to noise, such that it can only be due to microlensing, you know, this characteristic features that are only due to microlensing, or they're going to be events that, you know, have ground-based data where we know nothing else happened with that star. To the extent that we can tell over time, and you know, we're going to have to rely a little bit more on the quality, the higher quality, of hopefully higher quality of the Roman data relative to ground-based surveys, and then over time, as we get baselines in 5 years, you know, then we'll be able to rely more on those kinds of things. So, I think it's going to be an evolving kind of strategy over time.
So I was also trying to point out the parallax as well.
Yeah.
And another thing is from the ground-based analysis, most of the flares we can identify from the shape of the light paths. So that is only the case we have a good coverage and also good signal to noise. So the Roman can do much better job to discriminating. And so if we have a choice of the higher cadence, that would be helpful for removing such object. And so considering the discriminations, you know, the program may be there might be some unknown flare type with the time symmetric shape. So we don't know that kind of population yet. So probably the way is that we will have the statistical distribution of the flaring stars. So we expect some of the, distribution of the time scale and also the shape of the type of the flares. And if our free-floating candidates is within that kind of distribution, may be difficult to discriminate, but if there is a distinct population in the distribution, we may, separate from them. So we need to not study the flare by the Roman data or some other data set as well.
And I also want to mention, we have a lot, hopefully have much larger number of statistics. So, so these kinds of distinguishing between things based on statistical distributions would be easier. So for example, we could split the sample up in terms of the color type of the star, and we see that there's a different rate of free floating planets for different types of source stars, then we know something is up.
No more points? Right. No more points? Okay. So should we end this now and then thank all the speakers for today again and the runners with the microphones? They've done a great job.